You're funny looking too. You're the one
Healthy,
with the good
happy
hair.
babies are by far the most common outcome of birth in this country.
Peekaboo.
But about 3% of babies are born with some kind of physical or mental abnormality. Those are slim odds, but they're enough to bring a note of apprehension to pregnancy.
The more you read about having children, the more often you worry about what could go wrong.
Okay, why don't you step up on here?
To ease her mind, Linda Klippenstein has come for a diagnostic ultrasound, an easy way to see if her fetus is developing normally. Her doctor, Peter Dubélé, spreads a lubricating jelly on Linda's abdomen. He then uses a small wand that emits high-frequency sound waves. Like echoes off a canyon wall, echoes of the ultrasound waves are reflected from the fetus and displayed on a television screen.
There's one of the eyeballs, the top of the head. There's the baby's heart beating.
The pictures let Dr. Dubélé examine all the fetal body parts for structural abnormalities. The direct visual exam can also uncover the baby's sex.
It's a little boy.
It's a little boy! Nancy, you're going to have a little brother.
But the sex of the fetus isn't as important as its health. And to gauge that, a visual inspection isn't enough. Here, doctors rely on statistics, specifically inference on regression lines. The first step is measuring certain fetal body parts, such as the head, chest, and femur, or thigh bone.
This white stripe here is the baby's femur.
Freezing the image on the screen and using two cursors, Dr. Dubélé can get precise measurements of fetal body parts.
We can see that the femur measures 36.3 millimeters, which is approximately 1.5 inches.
Since fetal size varies, Dr. Dubélé uses a regression line with confidence intervals to tell him when a particular measurement signals trouble.
The solid line running along the screen represents the mean femur length as a function of gestational age.
In this case, the innermost dashed lines represent approximately 1 standard deviation from the mean. The outermost lines indicate approximately 2 standard deviations.
The femur measured 36.3 millimeters, which lies 1.2 standard deviations above the mean, which is within the acceptable range typically taken to be 2 standard deviations about the mean.
Statistical analysis of other fetal body parts confirms Dr. Dubelé's visual inspection. Linda's fetus seems perfectly normal.
From seeing the pictures, I'm sure I'll sleep better tonight. Feels really good. Let's see how to do prediction calculations using an example from the ultrasound story. We'll begin by predicting the mean thigh bone length of all fetuses at 25 weeks of age. We'll put the age of the fetus on the x-axis and length of the femur on the y-axis. Here is the regression line drawn from data gathered from a large sample of healthy fetuses. The predicted mean femur length based on this regression line is called mu hat. That differentiates it from the true mean given by the simple linear regression model we learned earlier. The predicted mean femur length for all fetuses 25 weeks old is just the point on the least squares line for x equals 25. You can find a rough answer by eye or a precise answer with this formula. Mu hat equals b naught plus b1 times x. In this case, our y-intercept, b naught, is 1.5, and the slope of the line, b1, is 0.12. Since x is 25, our predicted mean femur length is about 4.5 centimeters. Now, since we know there is variation in our estimate, we can get a confidence interval for this prediction. It's mu hat plus or minus t star times the estimated standard deviation of mu hat. This estimated standard deviation can be found using another mildly messy formula that's best calculated using a computer. In our example, S of mu hat is 0.31. Since we want 90% confidence and we have a large number of observations, our t-star value is about 1.6. Mu hat, the predicted mean thigh bone length, is 4.5 centimeters. So the interval is 4.5 centimeters plus or minus 0.5 centimeters. That's a narrow interval and reflects the large sample size and small scatter about the line. Now let's predict the thigh bone length we can expect for a single normally developing 25-week-old fetus. To do this, we use the same predicted response from the least squares line, except we call it y hat instead of mu hat because we're predicting one individual value instead of a population mean. Mu hat and y hat have identical values, but we use the different notations to remind us that in one case we're estimating a mean response, and in the other we're predicting an individual response. Since we just found that mu hat is 4.5 centimeters, y hat is also 4.5 centimeters. When we're estimating an individual response, we call our interval a prediction interval. It's given by this formula. Once again, S of y hat is best found using a computer. In this case, it's 0.75, which is more than twice the 0.31 we obtained for the estimated standard deviation of the mean response. So our prediction interval is 4.5 centimeters plus or minus 1.6 times 0.75, which is 4.5 centimeters plus or minus 1.2 centimeters. The prediction interval for an individual fetus is more than twice as wide as the confidence interval for the population mean. The difference between the confidence intervals for mean and individual responses is like the difference in the distribution of single values and the distribution of sample means. Remember that the distribution of the sample mean is always narrower than the distribution for single observations.